Yeah, welcome to the last talk of the session. Our last speaker is Angus Lowe, and he will talk about nearly tight bounds for testing tensor network states.
All right.
Three tensor network states.
Yeah, that's right. Thanks a lot, Jonas. Hello, everyone. It's great to be here. So as Jonas said, this talk is going to be about testing tensor network states, and it's based on joint work with Ben Lovitz. So my plan for this talk is roughly as follows. First, I'll begin with some background information, and then I'll describe our main result, which is a new lower bound for testing tree tensor network states. I expect this will take up roughly half the talk. And then I'll move on to proving the lower bound works for a specific algorithm before explaining why actually that lower bound is generally applicable because there is no better algorithm. And then I'll conclude with some final remarks. So first, let me set the scene. And I hope you'll forgive me if I end up repeating some things that have been said a few times this session. But imagine that you have some unknown quantum state psi, which is in a restricted class of states C, and your goal is to learn something about this unknown state. So here we typically imagine that there's some learner, Alice, who receives n identical copies of that unknown state and then performs some measurement on these copies in order to infer some property of this state. And the minimum number of n required to accomplish this task is known as the copy complexity. And now, as I've described it, this framework is sufficiently generic to encompass a wide range of important tasks in quantum information science, including shadow tomography and quantum sensing. In the case where Alice is interested in learning a full description of the unknown state, then this is known as quantum state tomography, which Alan spoke about earlier. And you could also ask a more basic question, which is whether psi is even in C to begin with. And this is the task that we're going to be focusing on for this talk, and it's known as quantum property testing. So in a little more detail, in quantum property testing, if the state psi is in your restricted class of states C, in other words, if it has the property, then we demand that the algorithm accepts with high probability. So here, the measurement operator capital M corresponds to the accept outcome for the algorithm. And this is known as completeness. On the other hand, if the state is far away from any state with the property, we instead require that the algorithm reject with high probability. And this is known as soundness. The algorithm is deemed successful if the completeness-soundness gap is at least some constant. And furthermore, we say it has perfect completeness if this completeness parameter A is equal to 1, which is equivalent to saying that the test always accepts given a state that's in this restricted class C. So on this slide, I've assembled a very non-exhaustive list of some prior work on various tasks in quantum property testing. On the right-hand side are tasks which require a number of copies that scales exponentially in the number of qubits that comprise your system. So based on the first talk of this session, maybe I should have put fermionic testing as well. But one example of a property that requires this number of copies is the task of state certification, where here the goal is to determine whether your unknown state is equal to some target state, some target mixed state, sigma, or whether it's far away from being so. On the other end of the spectrum are tasks which require only a constant number of copies to accomplish successfully. So for example, the product test of Haro and Montanaro uses just 2 copies of the unknown state to determine whether it's a product state on n qubits or far away from being so. And in this intermediate region, we have problems of an intermediate complexity. So for example, this genuine multipartite entanglement property is something we heard about earlier in the program during Adam Boulan's talk on the state hidden subgroup problem. The rank test is fairly self-explanatory. It's just testing whether or not a state has low rank. And the property testing task, which is most relevant for this talk, is that of the matrix product state test, which was introduced in this 2022 work by Soleimani, Farr, and Wright. And I'll explain that in further detail in the next few slides. But first, let me just highlight the fact that prior to our work, the copy complexity of these tasks was essentially settled, with the exception of this matrix product state test. And you can view one of the contributions of our work as putting the status of the copy complexity of this test on roughly the same footing as some of these other property testing tasks, up to some caveats, which I'll get into. Right, so first I should mention that tensor network states are an important class of states in physics, in condensed matter physics because oftentimes they serve as faithful approximations to the ground states of systems that are of physical interest. And more generally, they provide a means of representing slightly entangled states when you understand something about the structure of the entanglement. So how might you instantiate property testing for such a class of states? Well, for matrix product states, the relevant Hilbert space is a tensor product Hilbert space describing n qubits. And the restricted set C is the set of all states that look like this in tensor network notation. This is equivalent to saying that the amplitudes can be computed by multiplying matrices together, each of whose dimension is restricted to be at most r. Here, r is the bond dimension. And this turns out to be equivalent to yet another description, which is the set of all states whose Schmidt rank is bounded by r with respect to every edge on this 1D lattice. So if you understand what matrix product state testing is, it's sort of natural to generalize this to trees. So a tree tensor network state is the natural generalization of the previous setup for matrix product states, except here we no longer require that the graph be a 1D lattice. Instead, you can have an arbitrary tree graph. And we once again demand that the Schmidt rank is bounded by r with respect to every edge. OK, so that's a tree tensor network state. So I'll leave the description of the task at the top of this slide for your reference. And let me introduce our main results in the context of prior work. So if you set the bond dimension parameter to be equal to 1, then this is just product testing, because then all the Schmidt ranks are just at most 1. And in this case, a constant number of copies are both necessary and sufficient. But then in 2022, Soleimani, Farr, and Wright showed that as soon as you dial up the bond dimension to bond dimension 2, you get this sort of like phase transition in the copy complexity of this task, where suddenly you need like square root n copies, where n is the number of qubits in your system. And also they showed that n times r squared copies are sufficient. After this paper, there were a couple of follow-up papers which tried to close this roughly quadratic gap between the upper and lower bound. So in 2023, there is this paper on quantum pseudo-entanglement where one of their many corollaries was an improved lower bound on this task as a function of the bond dimension. And then in 2024, there was another follow-up work by Chen, Wang, and Zhang, which improved this bound a bit further. But notice that the scaling as a function of the number of qubits in your system remained square root. And then, so what do we show in our work? So if we show that if you're willing to let the bond dimension scales like logarithmically with the number of qubits that comprise your system, then actually a linear number of copies as a function of the number of qubits in your system are indeed necessary. And also nr squared copies suffice generally for any r. And this applies to any tree tensor network state in the setting of perfect completeness. That's the red asterisk. OK, so moving on to the proof of the lower bound for a specific algorithm. So the algorithm is pretty simple to describe in one sentence. It's just to apply the rank test to every edge in your graph. So what do I mean? Here, what you'll do is choose one edge in your graph and discard a subsystem corresponding to that edge from every copy of the state that you have. This results in a reduced density matrix on systems 1, 3, 4, and 5 in this case. And in fact, you get n copies of this reduced density matrix. And what you'll do is ask whether the rank of this reduced density matrix is at most r. And it's not too hard to see that this test has perfect completeness, because if your state was genuinely a tree tensor network state to begin with, then all of these ranks are indeed at most r. And what Soleimani, Farr, and Wright showed in their paper is that actually n times r squared copies are sufficient to detect if your state is far away from being a TTNS. OK, so we'd like to design a hard instance to prove a lower bound for this specific algorithm. One thing you should note is that unlike some related work, this hard instance is not a random ensemble of difficult states. Instead, it's a single state that comprises the hard instance. And how do you construct it? Well, what we'll do is we'll take a tensor product of bipartite states aligned roughly with the edges of the original graph that defined your tree tensor network. And each of these bipartite states will be an identical copy of the same state phi. And if you're a little confused about why there's like why there's triples of vertices on the right-hand side, but not on the left. You can just imagine that like the physical dimension of the central vertices on the left is like d cubed, so everything's consistent. So we'll take this state phi to have a Schmidt decomposition that looks like the following form, where most of the weight is just on the first pair of Schmidt vectors. And the first thing to note is that this state is genuinely far away from being a tree tensor network state. But it's not too hard to see that any reduced density matrix is actually quite close to being rank R. It's not rank R because the state as I've defined it has full rank, like rank D. But if you take like a partial sum of the squares of the Schmidt coefficients, it's pretty close to being rank R in that sense. And so this leads to the intuition that this rank test struggles to reject on this hard instance. And in order to quantify this intuition, I need to introduce rank testing. So here's a fact from representation theory. I think we've seen it once before in this session already. If you have n copies of a density matrix, you can always write it in this form, which is a direct sum over irreps, where the terms in the direct sum are labeled by partitions of capital N, which you can represent using Young diagrams. These are kind of like the quantum analog of sorted histograms. And it turns out that due to arguments based on symmetry, measuring these lambdas is optimal. And the optimal rank test is just to accept if the length of this partition is at most R. And in order to understand how well the rank test performs and quantify its performance, we'll want to understand the distribution over lambdas, which you can write like this. It's proportional to the lambda Schur polynomial evaluated on the spectrum of rho. And unless you're already familiar with the theory of symmetric functions, this might look like we've replaced one opaque-looking expression on the left with another opaque-looking expression on the right. So instead, what we're going to do is appeal to this nice theorem by O'Donnell and Wright, which says that if you're interested in computing the probability that the rank test accepts, what you can do is let P be the spectrum of rho, and imagine this hypothetical process where you roll a d-sided die, capital N times, distributed according to the spectrum of rho, and then compute the probability that the longest decreasing subsequence in this random word that you obtain from this hypothetical process is at most R. And so the upshot of this theorem is that you can replace this quantum problem with something that looks very classical and compute these probabilities to determine the probability that your rank test accepts. So how does the lower bound work? Well, recall the hard instance look like what I'm showing in the top right corner of the slide, and that the TTNS test performs the rank test with respect to every cut, with respect to every edge of the graph. So the acceptance probability is like the acceptance probability of the rank test raised to the power of the number of edges in your graph. And here I've just repeated what the theorem was in the previous slide. Here, the reduced density matrix, you can see from the vector of Schmidt coefficients, most of the weight is on the first Schmidt coefficient. And so what we'll get from this hypothetical process is a random n-letter word that looks like mostly ones. With probability 1 minus epsilon over n, you'll get a 1. But for the purposes of computing the longest decreasing subsequence, what really matters is the subword that starts with 8352 in this case. The ones are not so important for computing the LDS, and so we'll focus on that. And this subword is a uniformly random L-letter word. And uniformly random things are nice because then we can apply counting arguments to compute probabilities. And what you'll find in this case is something that should line up with your intuition, that the probability that you observe the longest decreasing subsequence being at most R is like very close to 1, unless the length of this subword y is like close to R squared. Okay. So now note that the length of the random word y is itself a random variable. It's like a binomial random variable with parameter epsilon over n, because with probability 1 minus epsilon over n, you see the letter 1. And then with probability epsilon over n, you see a different letter. And so suppose by way of contradiction that you took far too few samples, like less than nr squared over log n, then this expression I've denoted by a star is like very close to 1. And in fact, it's so close to 1 that amplifying by raising it to the power of the number of edges still results in an acceptance probability which is very close to 1. And this is bad, right? We've already established that this hard instance is genuinely far away from being a tree tensor network state, And yet we've computed that the acceptance probability of the test on this state is close to 1. So this is a false positive. So that's a lower bound for a specific algorithm. And now I'll explain why it's actually a general lower bound, because there is no better algorithm. And this is because it turns out I've been withholding information from you. If you care about testing pure states with perfect completeness, then there's just one test that you need to consider. It's this measurement operator here, given the projector onto the span of the n-fold tensor products of all the states in your property, which have your property. And you don't need to consider anything else. And usually this is not such a useful expression, but in our case it turns out to be kind of useful, because in tensor network notation we can write this projector onto the span of the set as follows, and it's not too hard to show that that projector is at least this other projector on the next line, which is like a tensor product of n copies of bipartite states. And zooming into that projector, we can rewrite it as follows, abandoning the tensor network notation. And this turns out to be exactly equal to the rank test applied to a subsystem within the symmetric subspace. And this is for representation theoretic reasons that have been known since at least 2007. And in fact, this equation that I've written down is emblematic of a more general fact, which is that in order to test properties of bipartite entanglement, purifications don't help. You might as well just discard Bob's system and then do spectrum testing on the reduced state. And you can see this in like a paper by Hayashi and Matsumoto in 2007, or in like Aram Harrow's thesis. And I guess in representation theoretic language, this happens because like the unitary group acting on A and the unitary group acting on B form what's called a dual reductive pair, at least with respect to the representation on the symmetric subspace. And this means a version of Schur-Wald duality applies in this case. Okay, so let me make some final remarks. So to summarize, we give nearly tight bounds for testing tree tensor network states, and as a special case, matrix product states, with perfect completeness when the bond dimension grows logarithmically. We also analyze few copy tests, where you're restricted to making measurements on few copies at a time, but I didn't discuss that here. And there are a few interesting open questions that arise from our work. So firstly, what happens at constant bond dimension? We suspect that square root n copies should suffice, but you'll have to ask me about that if you want to hear more. Another interesting question is what happens when you consider two-sided error. Note that we don't even know the answer for rank testing, so presumably you need to get the answer to that question first. What is the copy complexity of learning matrix product states? I think we know a polynomial number of copies should suffice, but nailing down the exact copy complexity is certainly an interesting problem. And finally, what is the copy complexity of learning and testing other tensor network states which may have like cycles in their underlying graph? And I think I'll stop there. Thanks for listening.
Thanks for the nice talk. It seems to me like you have to make an assumption that you know the graph of the tree tensor network state. Is that correct?
Yeah, that's right.
Okay. Do you have any ideas, or have you thought about whether you could learn if something was a tree tensor network state in general without already assuming you know the graph or the node ordering for an MPS?
Right. No, I haven't thought too much about that, but I think it's a really interesting question. I think this is sort of related to what Adam Boulon was talking about in his talk on the state hidden subgroup problem in terms of like identifying where the cut actually is with respect to which the state is product. But yeah, I don't really have any answers for tree tensor network states.
Okay, thanks.
So suppose you can measure two copies simultaneously, do you expect improvement?
Oh, so all of these algorithms work with giant measurements performed on all the copies simultaneously. I didn't consider restricting to measuring few copies at a time, but I can flip to a bonus slide that does describe that if you want.
Okay, thanks.
Kind of a follow-up question to the first question. So let's say that you think you know the graph and you test it using your method, and then
Mhm.
it's not a tree tensor network state given that graph connectivity.
Yeah.
It's still possible that it is a tree tensor network state just with a different connectivity. Is
That's
that
right.
correct?
Yeah, that's right.
Okay.
So you have to have some intuition about the underlying entanglement structure before you begin the test, I guess.
Okay, maybe we can relate this to the second talk. You say that you have large entangled measurements. Do you think there's a nice trade-off between the complexity for unentangled measurements and entangled measurements for MPS?
All right, thank you for asking that.
Okay.
So for few copy tests, we also consider these, and we're able to show that for tree tensor network states, okay, so firstly, maybe I shouldn't explain too much, but we have a theorem which applies in this case. If you're restricted to performing measurements on r+1 copies at a time, where r is your bond dimension, then we get an upper bound of like n to the r copies, which suffice, and a lower bound of at least n to the r-1 for such restricted measurements. But it's not such a nice trade-off as the one that Alan presented earlier.
Okay, that was an accident, by the way. That was not planned. Okay. Yeah. Okay, then let's thank the speaker again.